Hello everyone, my name is Mehdi Ousmane and I'm a PhD student from Université Catholique de Louvain in Belgium. Today I have the pleasure to present our recent work, recognizing 3D trajectories as 2D multi-stroke gestures. I will start with the introduction, then I will move on to the other parts. In a previous gesture elicitation study, we asked participants to elicit gestures that fit actions and commands to control objects in an IoT environment. As we can see in this video, some participants elicited 2D symbolic gestures in thin air. In the 3D space, we can represent gestures as sequential data of single point. In the literature, we call these kinds of gestures trajectories. Moreover, I would like to mention that there are several gesture recognizers for 2D or 3D gestures based on different techniques. For that reason, we raised in this work the question, can we recognize 3D trajectories as 2D multi-stroke gestures? Now I'd like to move to the challenges that we faced to answer the question. After conducting a targeted literature review on 2D stroke gesture recognizers, we selected 4 of them for multiple reasons, but mainly because they are simple as well as well-known recognizers. We cite the ones we have selected and which are Rubin's algorithm, $P, $Q, and $P+. Next, we extended these recognizers to 3 dimensions. Rubin 3D, a 3D version of Rubin's recognizer, formed of 3 2D Rubin recognizers. Rubin Chang, an extension of Rubin's recognizer to 3 dimensions. $P cube and $Q cube both are 3D versions of $P and $Q respectively. $F, an improved version of $P cube with a flexible cloud matching of $P+, $P plus cube 3D version of $P+. Finally, Freehand Uni, an improved version of $P cube with a flexible cloud matching of $P+. However, it differs from $F because the early abandonment is not included. After we created new 3D recognizers, we must prove their efficiency. Thus, we will experiment them in both user-independent and user-dependent scenarios, using 3 trajectories datasets. Furthermore, we tested recognizers for different conditions, which are defined by 2 variables, the number of templates and the number of points submitted. Now I would like to draw your attention to the total number of recognition trials performed, which is in total 665,000 recognition trials. We collected the test results through 2 quantitative measures, the recognition rate and the execution time. Thanks to the collected results, we can analyze the effect of 3 factors on the recognition rate and the execution time: the datasets, the number of templates, and the sampling. During this experimentation, we used 3 datasets. The first one is the SHREC 2019, a dataset proposed in a recent contest. The second dataset is the 2D TCGS. It was used in 3-sense recognizer evaluation. And the last one is 3D MATLAB SD, which is composed of 4 subsets or domains. In next slides, we present some examples of graphics and tables produced from test results on each dataset. Tables contain the recognition rate as well as the execution time values of every recognizer for the diverse conditions. The color scheme is defined by the median value in each table. We also generated a normalized balanced confusion matrix for the $P plus cube. We plot individual results for different conditions. In this slide, we can examine the average recognition rate for each recognizer on all datasets. In this diagram, as you can notice, $P plus cube has the best recognition rate with 87.48%. Even though this is a high recognition rate, the $P plus cube may have an even higher recognition rate. It depends on which dataset the recognizer is evaluated. For instance, with some datasets, the rate can exceed 90%. In the middle of the graph, we remark the dollar-like recognizers which have a similar rate, which is around 80%. At least we can observe that the Rubin 3D and the Rubin Chang have low recognition rates, under 70%. The SHREC 2019 and 3D TCGS datasets are evaluated only in the user-independent scenario. From what we view in these diagrams, the recognition rates are similar to the averaged recognition rates seen in the previous slide, except for Ruban 3D and Ruban Chang. In this slide, we take note of the difference between the user-independent and user-independent scenario. We observe a loss of nearly 10% for $P plus cube and around 20% for the other dollar-like recognizers. In these diagrams, we notice the low rates of all recognizers for domain 4. The principal cause is the type of gestures in this dataset. These figures indicate the recognition rates for all recognizers of the MATLAB SD in the user-independent and user-dependent scenarios. We remark significant difference when switching from user-dependent to the user-independent scenario, though there are some exceptions. Based on the results of the evaluation, we can say that the $P plus cube is the most efficient and effective recognizer most of the time. Ruban Chang should be avoided due to its low recognition rate and in all conditions compared to the other recognizers. Concerning the effect of factors on measures, we can cite the significant effect of the number of templates on the recognition rates of all the recognizers, the significant effect of the number of points on dollar-like recognizers. Likewise, the dataset significantly affect the recognition rates of all recognizers in the user-independent scenario. Now we come to the limitations of the experiment. Rejecting some recognizers have one kind of gestures to evaluate. Additionally, we didn't include the dataset size as factor to evaluate. To sum up, we made several 3D gesture recognizers based on 4 2D recognizers selected from the state-of-the-art. We implemented the testing framework in JavaScript and tested the recognizers. The test results showed that the $P plus cube provides excellent results. We have a list of some improvements for future work. We'd like to propose the effect of valuation of the depth variation in gesture. Moreover, we would suggest to compare with other recognizers based on other techniques. Thank you for listening.